Okay, in this video I'm going to go over Chapter 1. We're in Section 1.2 on series. So in 1.1 we had discussed sequences. So an example of a sequence is would be right here, which is the Bonacci sequence. Okay, so so I guess a sequence we can say is an output of a process involving infinitely many steps, and then a series sums them up. Okay, so here's your Fibonacci sequence. Here's an example of a summation, a partial sums summation, if you limit it between 0 and 8 of the numbers in the Fibonacci sequence. Okay, generally discussions about series tend to revolve around whether the series has an ending point, or whether it converges on a certain number, or whether it doesn't. So generally it's difficult to determine that. However, a special kind of series, which is the geometric series, that allows us to determine this, and we'll do it mathematically. So that's what's coming in this section. Okay, in the next page we're going to talk about this intriguing number, 0.9 bar notation, and what it actually means. Alright, so you're familiar, I'm sure, with bar notation. So the bars over the number that repeats in a decimal number. So things that you want to notice. This number, or really any bar notation number, is really a summation. So that means it's really a series. So look what it really is. It's a geometric series, since 0.9 equals 9/10 plus 9/100 plus 9/1000. So if you think about it this way as a series, then you can use that knowledge to rewrite it as a fraction. So this is how you do it. If your repeating decimal is in the 10th spot, take your number and multiply it by 10. In this situation, that gives us 9.9. Then subtract away the repeating part of it by subtracting away 1x. So I've set x equal to 0.9 bar notation. Okay? So if I subtract 10x minus x, I get 9x. And if I subtract 9.9 bar notation minus 0.9 bar notation, I get a plain old 9. So what does my x actually equal? Divide both sides by 9, and I find that my x actually equals 9 over 9, or 1. So when you think about 0.9 with bar notation as a geometric series, and it's a summation of this geometric series, then you can see that your number converges on 1. Alright, so this was a geometric sequence with a multiplier of 9/10. So that's what was happening there. So let's go on to the next page. Okay, so I just caught a typo. So this 9/10 is not the multiplier. So you probably said, why did she say that? So I'll correct it on the hard copy so you won't even see this again. But that multiplier is actually 1/10. So to go from 9/10 to 9/100, you multiply by 1/10. To go from 9/100 to 9/1000, you multiply by 1/10. So your R equals 1/10, and we're going to learn later on that as long as R has an absolute value that's less than 1, your series will converge to a number. And in this case, our number is 1. Alright, now we're ready to go on to the next page. Alright, so we can denote the sum of the first n terms in the sequence by this expression. So the Sn means that we are taking a partial sum. Okay, partial sum. We're not taking it all the way to the end of the sequence. Alright, so this is telling us this is a summation called sigma. It looks like a fancy E. So I starts at 1 and it goes to n. So if we're going to work with this, what we're going to say is 9, so this will be 9/10 when I is 1, 9/100 when n is 2, 9/1000 when n is 3, and so on. So depending on what your n is, you will have either the sum to infinity, or you'll have a partial sum. And as I said previously, since this was just the fancy number 0.9 bar notation, this was a convergent series, which means that it converged to one number, and that number was 1. All right, here's our theorem now. So the theorem for 1.21 says the geometric series conversion theorem. So for any non-zero real number a, so a would be the first in the series, the geometric series converges to the sum a over 1 minus r, where r is the ratio, if the absolute value of r is less than 1, and it diverges if the absolute value of r was greater than or equal to 1. Okay, so think about that. I've already told you that the 0.9 bar notation converged, and I referenced the fact that the absolute value of r was indeed less than 1. Okay, so think about that, and we're going to move on to the practice problem. Now, before I go into these practice problems, why don't we use the 0.9 bar notation that we just worked on a second ago and see why it converges. So 0.9 was my bar notation. That was my first term. I can also write that as 9/10. So let's use this equation, and we're going to have 9/10 over 1 minus r. Now, r was 1/10, so this is 9/10 over 9/10, which equals 1. All right? So we said that that sum converged to 1 just by doing the fancy algebra procedure of multiplying that initial a value by 10 and then subtracting away one of the x's and turning it into a fraction. But we also could have figured out what it converged to by using this formula. And because your absolute value of r was 1/10, the absolute value of 1/10 is 1/10, and since this is less than 1, it makes perfect sense that that does indeed converge, and it converges to 1. Okay, now let's work on the practice problems on the next page. Alright, in this practice problem number 1, it says to use 1.21 example above, not the theorem, to write 0.41 bar notation as a fraction. So let's go back and see what we're going to use. So we are going to use, let's see, go back one more. We're going to use this computation. So this gets used in the problem that we're addressing right now. Okay, so I'm looking at it, and my A, okay, so my A equals 0.41 bar notation. What you want to know is if you want to turn that into a fraction, this is what we're going to do. We're going to notice that the bar notation comprises 2 decimal points. Okay, it comprises out to the 100th spot. So since that's the case, your algebra is going to be taking this value, and I'm going to make this, let me make this an x to be consistent with what we had before. So here's my x. So we're going to say not 10x because I don't have 0.9, which is only to the 10th. I have 0.41, which is to the 100th. So I'm going to say 100x, and that's going to equal 0.41 times 100, which equals 41.41 41 bar notation. Then I'm going to subtract away an x, and so I'm going to subtract away a 0.41 bar notation. Alright, so when I do that subtraction on the right side, I get the whole number 41. When I do that subtraction on the left side, I get 99x, because I had 100x minus 1x. So now I have 99x, equals 41. So therefore, what fraction can x, which was 0.41 bar notation, equal? So that's going to equal 41 over 99, and that's how you do that type of problem. Okay, let's go and we'll do another problem similar to this in number 2. Okay, in example 2, we're going to do the same procedure where I want to write a bar notation decimal as a fraction. So since I noticed the bar notation goes out to the thousandth spot, I'm going to multiply my x, which I'm defining as 0.574 bar notation, by 1,000. So I'm going to say 1,000 okay, my little stylus is not working, so let me see if I can get this working. Okay, we're back working. So I'm going to say 1,000 x is going to equal 574.574 bar notation. And then I'm going to take away, let's see what I want to do. I want to take away the repeating part, so that is just x. So I'm going to subtract away the x, and that subtracts away the 0.574 bar notation. When I do the subtraction on the left, I get 999x, and on the right, I get a whole number. Divide by 999 on both sides, and I get an expression for x, which was 0.574 bar notation, an expression as a fraction, and that fraction cannot be simplified. If it could, I would go ahead and do it. So that's our answer there. Okay, I have one more of these examples, and we'll do that on the next slide. Okay, so look at this number. The number I want to turn into a mixed number or an improper fraction is right here. Now, I didn't put the bar notation, so I should have put it over the 0.45. So that's the part that is repeating, and so I'll fix that on my hard copy that I have posted. All right, so where does that start? Well, not the 10th, and where does it start and finish? Not the 100th, not the 1,000th, not the 10,000th, but the 100,000. So for that reason, I'm going to multiply the x, which I'm defining as this number that's underlined in orange, and I'm going to say that 100,000 times that x, that's going to be 112345.45 bar notation. Alright, now, this is a little bit tricky because I need to multiply the x by a number such that I can subtract away the repeating decimal. So, let's work backwards. I want it to be, point, and that's just a dot, 0.45. So what should I multiply it by? So 45 is there. I would like to have 1, 2, 3 be on the other side of the decimal. So that's 10 times it, 100 times it, 1,000 times it. So I'm going to multiply my x by 1,000x. So the number I have in front of the decimal is going to be 1123. So this is 1123. And I'm subtracting it. On the left-hand side, 100,000 minus 1,000 gives me 99 11,000x. Subtracting these two terms, I end up getting 1, 1, 1, 2, 2, and then there is no value after the decimal because I wanted to get rid of that, and I have successfully done that. So let me just scoot this over. So that's what I have. So I now want this to be a fraction. So divide both sides by 99000, and this is 11,000, so this is 90, this is 111,000. No, this is 11,000 over 99000. Okay, hold on, because I just found something. So let me just erase one thing and fix this. When I did this, whoops, when I did this subtraction, hold on, I have to do some fancy stuff here. Okay, got it. When I did that subtraction, I should have gotten 1, 1, 1, 2, 2, 2. I just dropped out a 2. So that's what I have over 99,000. Now, I should notice that that's a mixed, or that's an improper fraction. That should not be a surprise. The number that I've been working with is a number greater than 1. So my fraction has to be an improper fraction. So I'm going to rewrite that as a mixed number, and 99,000 can go into 111,222 one time. So this is going to equal 1, and 12,222 over 99,000. Now this time this fraction can be reduced, so you can use your graphing calculator to do that. Just use that math function and get the new fraction, and that's my new fraction. So if I want to write a repeating decimal number as a fraction that is reduced to simplest terms, this is the procedure that I will follow. So go back, make sure that that's clear to you, and we're going to a different type of problem in number 4. So in this next problem, number 4, it says consider the series 2 plus 4 plus 8 plus 16 plus ... So it's continuing. Use theorem 1.21 and determine if this series diverges or converges. If it converges, find its sum. So let's flip back a little bit and let's look at that theorem. So here is the theorem coming up right here. Let's see if I can get it. So here's the theorem, and I'm going to just change my color for a second. So here's how they are presenting my series. And then they talk about these terms and how to tell what it converges to. And so we're going to use this terminology in this next problem. So let's go back and we'll now get to it. Okay, so this is written 2 plus 4 plus 8 plus 16. So this had been a sequence. So what was the sequence earlier? Well, that sequence was 2, 4, 8, 16. So how do you figure out what's going on there? Well, think about that theorem. That theorem had expressed the series as A plus AR plus AR squared. If we can determine our A's and our R's, and then ... then we can use the formula to see whether it converges, because I'm going to evaluate my R, my absolute value of R. So if A is 2 plus A is 2 again, it looks like R is going to be 4. Let's make sure that works. Plus 2 again, and then 4 squared. So I do indeed get 8 here, and I get 16 times 2. So will I get what I need to get? And the answer is yes. hold on, I've lost my head. So I'm just going to backtrack a little bit. So we have our A. If I want to get 4 from that second term, my R should be 2. Now we're on track. So here's my A again was 2. If I use my R as 2 squared, which is 4 times 2 is 8, so yes, I am seeing that pattern. So now I want to think about a couple of things. Again, I'm looking at my theorem, and my theorem tells me that my series will converge to the sum, which can be expressed as A over 1 minus R, if the absolute value of R is less than 1. Well, what's my absolute value of R? My absolute value of R ends up being 2, so R equals 2, and that is the absolute value, because the absolute value of 2 is just 2. So am I going to converge or diverge? So since I do not have this, okay, I don't have that, my series is going to diverge, and I'm done with the problem because I can't find what number it converges to because it's not converging. Okay, we're going to have more opportunities to practice things that do indeed converge on the next page. Alright, so in this page, I'm seeing I have the series 2/3 plus 2/9 plus 2/27 plus 2 over 81. So previously, in section 1.1, this would have been the sequence 2/3, 2/9, 2/27, 2/81. And I would have said, oh, that's geometric, and let's figure out why. All right, remember you want to put it into the A plus AR plus AR squared series generic formation so that we can pick out our A's and our R's. So if A is 2/3, then using A again, I will multiply by 1/3 to get R. So 1/3 would be R. Is that true? That's 2/9, so we're good. Now if we continue, is that going to work? 2/3, okay, 1 over 3 squared is 1 over 9, and yes, that's giving us what I need. So I now know I can define my A equals 2/3, and my R is going to equal 1/3. Now if the absolute value of R is less than or equal to 1, I'm going to have a situation where the sum of the series will indeed converge. So I do have that. I know it's going to converge. Let's figure out where. That's when I say it converges to some number, and I can arrive at that number by using A over 1 minus R to get that number. Okay, my A was 2/3. My R, let me put that denominator. My R was 1/3. So what's 1 minus 1/3? That's 2/3 again. So what I'm seeing is that this number converges when you add the series to the number 1. So my series converges, and it converges to 1. All right? So let's go on to the next one. It's another fraction example. Okay, in this last example, I have a series that alternates between positives and negatives. So I know that my A in this situation is going to be negative 1/4. So what do you think your R is going to be? If AR has to equal 1 over 16 and A is negative 1/4, it looks to me like my R is also going to be negative 1/4, and I would test that further to make sure that it works every single time. Alright, so I have A is negative 1/4, I have R is also negative 1/4. What do you think about whether this series will diverge or converge? So, looking at the R, what's our rule? As long as the absolute value of R is less than 1, then I'm going to converge. Well, the absolute value of r will be 1/4. That's less than 1, so yes, it's going to converge. So let's figure out where it converges. So if you add up all the terms, what will you get to? So that formula is just a over 1 minus r. So I have negative 1/4 over 1 minus a minus 1/4. Okay, that's negative 1/4 over 5/4. Negative 1/4. I never really divide by fractions. I multiply by the reciprocal. So I'm going to get, and that's a positive, so I'm going to converge at negative 1/5. Okay, so my series converges, and it converges at negative 1/5. Okay, the last slide we're going to talk about the other items that you need to understand for this section. All right, so we'll do that on the next page. Okay, so here's a couple of more things from this section that you need to understand. If you're asked to find out the sum of the first n consecutive terms in an arithmetic sequence, and they give you a first term a and a common difference, then you can use these formulas to figure that out. All right, so a couple of things. They may not give you a and the common difference. You may have to work towards it. So look at the types of equations you have in this section. I put it on the first page of the problem set. And you may need to combine some equations, kind of like what we did in class last time, to determine missing numbers so that you can indeed get a and the common difference. Okay, so if you're going to do anything with arithmetic sequence, and have it be the sum of the first terms, that's adding up an arithmetic series, you're going to do this. Okay, those would be the equations you're looking at. I said be comfortable putting a series into summation notation. Okay, notice where your i's start. I equals 1 to n. Be familiar with these. I'm going to give you the equations on problem sets and assessments, so I'm just testing application, but you may have to play around with this a little bit until you get comfortable. Okay, so then down below it says the sum of the first n consecutive terms. So I don't want to know if this series converges or diverges. I want to add up the first n terms. This is a partial sum. So to get that, for a geometric sequence, this is what I use. All right? So be familiar with this, know that it's out there, and practice applying these techniques in your problem set.